All right, guys. So what is up? So we're gonna go through the most recent Codeforces contest, the Div 3 round. And yeah, I've been keeping up with previous contests, and the most annoying thing is I haven't been able to take these contests because I've had like work or like church on Sunday. So it's like, bro, and it's really annoying because I've actually been doing like pretty consistently well on these contests. And the last contest I took was my worst contest ever. But like if I took all these contests that I missed and I know my rating, like I'm smurfing my rating right now, which is really funny, but it's whatever. So we're just gonna go through this problem set. My thoughts on this problem set were was okay. Loki was a straightforward problem set. I only had issues on C because I just trolled C, but in hindsight it's really not that hard. I just like I just trolled it. But yeah, A was straightforward, B was straightforward. D and E were really straightforward questions. Like I would yeah, I don't know. D and E were just super straightforward. Like the way that I'm going to explain them, you're gonna be like, oh, this is like straightforward. So maybe I don't know. So let's just start with problem A. Forgot what A was. Oh yeah, so choose a random index and if A sub I is greater than B sub I, so if the element is over it, then you decrease it by one to get it closer to B sub I. But if it's under it, you increase it by one to get it closer to B sub I. And you basically stop, like you cannot do operations. Um, Yeah, you stop the iterations if there is no element that is over B sub I. So yeah, this is like a funny question because it's like I mean you can try a test case. So let's try a test case here, but you can also mentally solve it. Definitely, this is mentally solvable. And it's actually good practice to mentally solve problem A's because you got to be quick with them. But for this one, it's like any value that is over B sub I. So I'm gonna select these pairs. So these are the pairs that are over B sub I, like A sub I is over B sub I. Regardless of what you do, you're going to need three iterations from this pair and three iterations from that pair, regardless of what you do, because you're always going to do an iteration as long as those values stay over A sub I. So you need at least three plus three iterations. And then you're going to need to find let's see. Oh yeah, then you need another iteration after to check if there's any pair that's greater than B sub I. And if there's not, you ignore the step. And then so you need that one iteration, which is called like the check iteration. To just check, after all these pairs are resolved, they go down to one, they go down to one. You still need to check these pairs. So that's like that extra iteration at the end to just check if all the pairs are like now not if there's any pair that's has an A sub I value that's over B sub I. And so that's what this is, right? So basically, like you realize that for example, any pair such that A sub I is equal to B sub I, those pairs they don't matter. You can treat them like they don't even exist because you won't even they don't they're irrelevant, and then anything that's under it, like you're gonna increase it by one, but you know that any pair such that A sub I is less than B sub I, right? Whoops, what? Okay, any pair such that A sub I is less than B sub I, you know that you'll never be able to switch the inequality to this, right? Like it's always going to be less than or equal to, right? At all states. And so that also doesn't matter at all. Um, so basically the solution is this. You just, you start off, this is the checking iteration, the one additional you need, and then you just uh take maximum zero A sub I, B sub I. This is basically a trick to say like if this is negative, uh add zero, but then if it's positive, um, add the positive amount. So yeah, this is basically the solution. Yep, so straightforward. Okay, this one actually I thought B. To be honest, I personally I'm not sure. Maybe the editorial has a better way of thinking of it, but I thought this was low key like. In fact, to be honest, I think B is like just as difficult as E. I'm not even going to lie. B is just as difficult as E, in my opinion. Um, In fact, I can make the argument that B is probably harder than E because Once I read E, I instantly solved the problem. But B was like I actually had to think more. Maybe I don't know. I thought both of them are straightforward, but I would say that B is probably a harder problem than E. And most people just would not think that because he's further down the problem set, but it's whatever. So you're given an integer n, and basically for all I, okay, you call an array good if the product of adjacent, like if every pair of elements, as long as like their product is less than zero, then you're good. And then for all subarrays with at least length two, the sum of all elements in a subarray is positive. So that's what an array is good. So basically, the first condition just translates. So a lot of times code forces will give you like you know they'll give you conditions that are not concrete, okay? So you need to make them more concrete. You need to translate them into a more concrete form. So concretely, the first condition is just saying that every pair of adjacent elements has a different sign. So that's more of a concise definition. That's more specific than just saying that product is less than zero, right? That's not as precise as just saying every pair of elements have a different sign. So first, that's what you need to understand. That's what the first condition means. And then the second condition is saying that, okay, um, for all subarrays with at least length 2, the sum of all elements in the subarray is positive. So here's a interesting thing is, so let's say we have a subarray of length 2, and you know it says at least length 2, but maybe we only have to check subarrays of length 2. So that might be a question you might have. Like, do you have to check this, or I don't know this, I don't know, but that condition, at least as of right now, it's as concrete as you can possibly get. So, but the first condition we made it concrete. Now, there's one trick in this problem, or one like little thing asterisk is, an array A is better than another good array B, as long as like A is lexicographically smaller than B, and it's a fancy way of saying like A is like more alphabetically sorted. So like for example, Fiki, and so if I say Fiki versus Fun, right? Like this is more lexicographically sorted because it's like if you were to sort like names of an alphabet, that's what lexicographically smaller means. And then for numbers, it's the same thing, right? Like 1, 2, 3, 1, 3, 2. This is like lexicographically better because it would appear first. So that's all they're saying. So uh, now this problem, here was my mindset of how I solved the problem. And yeah, I thought this was actually a more difficult problem. Uh, so you first see that for the construction for two, the best sequence, so you want to print out the best sequence. By the way, it says output a good array that is better than every good array. So basically the lexicographically smallest sequence, so the best sequence. So the way that I solved this was, so look at -1 and 2, right? And well, so this is the best sequence. Now if I have the best sequence, I want to say, how can I take the best sequence? So for n equals 2, and then say, okay, if I have the best sequence for n equals 2, how will this work for n equals 3? Basically, it's kind of like a DP-ish mindset where you say, if I have the best sequence for the first I elements, right, for numbers from 1 to I, what is the transition to I plus 1? That's the mindset. With this mindset, you'll be able to solve the problem because this is the exact mindset that I had. And you notice that it's not too bad. So, for example, so I have the best sequence for 2, and I want to see, well, how would I transition from this to this? So now you think about it like this: -1 to 2, and you want this to be lexicographically smaller. So you might say, well, why can't I just put -1 here? Um, because this would be lexicographically smaller than this. But you realize that if you take first of all, you have to understand that if I just append -1 for n equals 3, you have to understand that every subarray here, like, before this line, all of those subarrays, the good thing is that, like, we know they satisfy this condition. They satisfy all the conditions, So all those so you only have to worry about subarrays that end on this new element. Um, and we know that if I make it a different sign, Like I make it a different sign than two, I'm good. So I satisfy that condition. But then I have to worry about this condition, all the subarrays, ending on the last element that I append. I have to worry that, do I have a positive sum? And think about it like this. Well, the only subarray that I would care about is the subarray that has the minimum value in sum. I would want to check, okay, so what subarray ending on the new element or ending on I plus one, I guess, is going to give me the minimum subarray sum. And I want to check if that's still positive. That's what I would check. And so if you think about it, if I go here, the question is, okay, this is my subarray sum. Um, do I and I check here. So this is positive, and then I do another negative guy. Okay. And then the question is this, right? This is the subarray you should check, right? Now, if you have like I plus one elements, let's say you had I plus one elements here, and this is just I plus one elements, then you have like maybe I minus one. This is the subarray. This is the minimum subarray sum. And you can prove this because think about it. If Okay, so this is like for odd. Let's say we have like an odd n is odd, right? Like if I add more things, like if I add this, it's gonna be positive, so that's gonna increase it. But then if I add this, the sum of this is positive. The sum of these two elements is positive. So I know I'm just gonna increase the subarray sum. So I know that the minimum subarray sum will just be the last three elements. It's gonna be the last three elements. So all I have to do is check if that's positive, and you realize that in this case it's not -1, 2, -1. So that's gonna sum up to zero. So you fix this by making this three. You fix this by making this three, right? And then now you ask yourself, okay, well then, no, this is n equals three. How do I make n equals four? Well, the idea is that you have to make it positive, but you can't make this one, otherwise you're cooked. So because the sum of this and this is gonna be zero. So what you do is you make this two, and you realize that if you put a positive element here, all the subarrays before this, it passes these two conditions, and then you only have to worry about the condition of like subarrays ending on the new element you appended, and you realize that it's going to pass all the conditions for all previous subarrays, right? They were already positive, so now if you appended a positive element, it's still going to be positive, so you're good. So then you can put two here, and then if you try to do n equals five, it's like you realize that okay, let's say I try to do n equals 5. So this is n equals 4. Okay. So for n equals 5, you might be like, okay, what can I do? Well, I'm going to try to append -1, but then I have to check the last three elements, and I realize that they sum up to 0. Um, and so I just change this to 3, right? This has to be changed to 3. There's nothing more you can do. And then you realize that yeah, it's just. But then so basically you realize a pattern. You realize that for odd lengths, it's just alternating between -1, 3, -1, 3, -1. But then if it's even, you just append it to. So that's what it is. So it's just like this strategy. So what we're gonna do is that if it's odd, we just alternate between -1, 3, and -1, 3. But then if it's even, we just print out a two at the end. I'm sure you can like make this more concise. You don't need this if statement, but I don't know. I sort of. Yeah, there's probably like a easier way to implement this. So the easier way would just probably be uh maybe it would just be like so you want to do that an odd amount of times. Actually, not whatever. I don't care about that. Okay, whatever. There's probably an easier way to implement this, but I just thought of like copy paste. Um, but it doesn't really matter. So yeah, this is just the code. All right, problem C. This is funny because problem C, I made this deeper than it actually was. I actually want to see, bro. What? Why did I troll this question? So my first submission. Yeah, I had the idea. What was I doing, bro? I have no idea what I was doing. To be honest with you, maybe I just needed to think about the question more. This was like an O of K solution. I completely forgot that you can't do O of K. Yeah, but then I got it right. So, whatever. I guess it's like a kind of a fumble. But for this question, so you're given two multisets, and you know you can perform an operation on one of these, which is S, and you can basically change an element in the multiset to be X plus K, or you can subtract K and then take the absolute value. So if it goes under zero, then we just make it positive. So for this, like you need to make sure, like again, like I said, anytime they give you some operation, usually it's not as straightforward, and so you need to make it concrete. So translate it. So this is like what I've noticed in a lot of problems is just translating like conditions and making them more straightforward because code forces will, I don't know why they always just make conditions not straightforward. I guess that's like the problem solving kind of. You need to be able to say like I don't know. So in this case, like if I say like I can take an element and I can just add it k times, I'm basically just saying that for any element, I can make x into y as long as x is congruent to y mod k. That's what it's saying, right? Like as long as x y, like I can make x into y as long as it's congruent to y mod k. And the assumption is that x and y are positive. So for this element, what I'm going to do is that x and y, as long as they're congruent to mod k, then you can achieve x to y. And just as long as it's equal to mod k. That's the definition of modulo. So, you can consider these elements in mod k. It'll be easier for you. So consider all these elements in mod k, and now, yeah. So now that's just this x plus k condition. What does this x minus k condition mean? So basically to reduce the problem, I'm gonna assume that all these elements are now being reduced by mod k. That doesn't affect the problem. It just reduces it. So this would just be this translates to, so if you this was it was mod 5, so this would be 1 2 4. This is like 3 4 4 1. So you can already see that 1 and 1 should be paired and 4 and 4 should be paired. Now 2 and 3, how are they paired? Well, what you do is you subtract k, and then this is -3, and then you make an absolute value, and that's 3. So you subtract the k. So basically, if you have some remainder and you subtract k and then take the absolute value, it's the same thing as just k minus r modulo k. So it's just k minus r modulo k. And so basically, the observation is that every element can either be, so every element is some remainder. So it's just, so so we've reduced everything mod k. So every element is just a remainder. So it's this, and the idea is that every element, so every element can either be r or k minus r mod k, because what you can do is you can subtract k and then absolute value it and then mod k it, and so every value can be this. So then you can just think of like having a bunch of pairs where you have a bunch of pairs, and so for example, this would be, well, I don't really want to do it, but you have a bunch of pairs basically, actually. So you have a bunch of pairs now. So A1, A2, A1, B1. Yeah, you basically have a bunch of pairs, and you want to see, like, and two pairs can be matched up. So let's say you have a pair like X1, Y1, and X2, Y2. And as long as you have a value, like as long as like, two pairs are going to be matched up, as long as like, you know, as long as like uh the set of them are the same. So we don't care about the order, right? So for example, it could be like 4 6 and it could be 6 4. Yeah, like as long as they both contain the same elements, then we can match them up. So the only issue here is that for these pairs, we don't want to care about order, right? We just want to care about the fact that you have those elements. So what you do is, for every pair, that 4 will always be paired with 6, and 6 will always be paired with 4 because of this like formula r k minus r. They come in pairs, right? So what you can do is you can compress each pair into its maximum value. compress each pair into its maximum value. So just take the maximum of these, and you could just change this to be the maximum of these, and then just see if the multisets are the same. So that's exactly what this is. Yeah. I don't know why. Don't ask me why I trolled. I mean, I figured it out, but don't ask me why I trolled. It was like funny. Okay, so now D. I think my favorite problem on this. Looking at my favorite. I think my favorite problem was B. I'm gonna be honest. D and E are just. I don't know. They are the hard. This one again. They always try to scare you with like these problems, but they're like I'll show you the implementation. I'm not trying to say like I'm a genius. I'm just saying like this is the mindset you also need to be able to solve some problems. Is you can't really overestimate their difficulty. Like this is not. It's not. You don't even need DFS on this problem. Like you might think, oh, I need a DFS. I need to iterate through this. No, you don't, bro. Okay, so um, in this question, you have this tree, and what's going on is that in one operation, you can choose some path, cut off all the edges, and then for all those nodes, just reconnect them to the starting node, right? So it's they show you right, cut off all these edges from 3 to 4, and then connect them to 3. And the question is to minimize the diameter. You want to help determine the number of operations to achieve the minimal diameter. So basically, here's the translation of my condition. I made it more concrete. Here's what basically made me solve the problem very easily. Is minimize the diameter is the same thing as saying make this graph into a sunflower. This is a graph like this will always have a diameter of n equals 2. Well, unless the graph is, the edge case is this, right? Unless it's just this. This is like, but other than that, you can always achieve a diameter of 2. Like a graph that has a diameter of 2 is a sunflower, I guess. Yeah, a graph that has a diameter of 2 is a sunflower. I don't see what's wrong with that. Is that always true? Seems right. So basically, you want the graph to have a diameter of 2, otherwise you want it to be a sunflower. So like there's one central node and there's like other nodes that emanate from it. It's a sunflower. So that's basically what this condition is. And so then the question is, what should be the center? So first, the question is, what should be the center of my sunflower? How should I determine what is the center of my sunflower? So I actually called it the root, but it should be yeah, you can call it the root, but in this case, it might be more intuitive to call it like the center of the sunflower. So it turns out that, you know, for your sunflower, the number of operations you need is going to be the number of leaves that are not already connected to the center, right? That's the number of operations you need. So basically, you want to choose the center that has the most amount of leaf connections, right? Because, for example, if you have some leaf, for example, let's say this is a graph, right? So some leaf that's not connected, you're gonna have to like, choose this path and connect everything back to this in order to fix it up, right? So basically, for some selected center that you want, the answer for that center is basically the number of leaves that are not connected um, to the center, and once you observe that, then it's very obvious of what center you should choose. You should just choose the center that has the most amount of leaf connections, and then the answer, it's easy. There's no DFS required. um I just, I iterate, count the number of leaf connections. So this is basically just the number of nodes with size 1, and that's the number of leaf connections, right? So I go iterate through all the, connections and check, if they only have one connection, that's a leaf. And then, I say, well, I'm going to make the center of my sunflower, or I guess the root, I call it the root, should be maybe center. I'm going to make the center, I'm going to make that the center. And then, all I have to do is iterate and say, okay, are you a leaf and are you not connected to me? I need an additional operation. Print out. Simple, right? So that's it. Okay, this one also simple too. Like this is also simple. There's not a massive explanation for this one. Um, So you can perform the operation at most once. So for this one, like I thought of just iterating backwards immediately, and I solved the problem because you realize like if you so I just needed one test case and I solved and the problem was solved, right? Because the thing is right, like you're gonna say like, okay, can I get 4 to 1? And basically, it's like you can get to get 4 to 1. You might think of like, well, what are all the possible elements that a sub I could be, or a sub I plus one could be, right? Like for example, if I'm trying to get some element, you know, so if I'm trying to get some element, to b sub I, then I can only use a sub I plus one. I can only XOR it or not XOR it, and then those are the only two things that I can do, right? But the trick is like, well, I need to know what's the set of all possible values that a sub I plus one could have been, because I could have also changed this value by using this one too, right? So you don't really know, right? So the trick is you actually go backwards because you know that like for this four, bro, like this element is gonna stay five no matter what. So you know that either you can XOR it with five or you don't XOR it with five. And then, so then after that, you know that you need to XOR it with five to get one, I think. Yeah. But then you realize for this one, the options that all the possible elements that this could have been was four or one. Like those were all the states that a sub I plus one could have been in. And whenever it was in one of the states, four and one, in this case, you need it to be four, you would have just already XORed three with that four, and that would have been seven. So basically, all I'm saying is keep track of all the possible options that could have, for the elements for, so you go backwards and, for a sub I plus one, keep track of all the possible options that it could have been. And, there's a trick of like, you might not want to actually XOR it. You might want to keep it the same. What I do is I just have a third option that's zero because the XOR of some element in zero is itself. So it's like not changing it. So that's my third option. Otherwise, you could have XORed it with a sub I or b sub I. Like the possible states for a sub I plus one are itself and the element that it wants to get to, right? Options represents the options of the element ahead of it. That's why I set it down here. um, and so yeah, it could have either been itself or the element there. Those are the possible states it could have been on, and all you have to do is just like pass, as long as like you find one option that works and it's true, and then you break it out and say print it out. Yeah, so I don't know about F. I looked at F. I was like, yo, only like 2K solved it. And I don't know. There's some D's that I have to upsolve, so I'm probably not gonna do it. Yeah, maybe I'll do it, but for now I have some D's that I need to upsolve. But anyways, I should probably do it actually. I'm not gonna lie, because I mean I was able to solve A3, so why would I not continue on to the next problem? Yeah, but not today. Probably maybe another day. But anyways, that's it.